So if you think your gas cleaning plant is just a filter, you're missing half the chemistry occurring at the top of your furnace. So today we are dividing deep into the classifier engine, specifically the mechanics of dry GCP dust breakup. For a particular dimension, maybe something like 1,000 to 1,050 meter cube blast furnace. So as a senior project engineer, you know that managing the dust burden is an much about chemical partitioning mm, as it is about environmental compliance. By the end of this session, you will gain three key technical deliverables. First, a granular understanding of 50-50 physical fracture between the cores and the fine dust. Second, the thermodynamics driving zinc migration to the baghouse. And third, how the specific spatial advantage of dry system enables high value recycling pathway. So looking at the wireframe on your title slide, follow the gas flow from the furnace uh, through the primary and secondary cleaning stages. So this architecture is the heart of a closed loop iron making system. To understand the dust, we must first define the baseline operational patterns that generate it. So coming to uh, our journey further, moving forward. So let's look at the uh, baseline operating envelope for our 1050 meter cube furnace. The gauge on the top left shows our effective volume and a steady state hot metal output of around 113 ton hot metal per hour. On the right, the pulse wave graphic indicates a massive gas flow of 340,000 normal cubic meters per hour with a top pressure of 1.4 to 1.7 kPa. Now look at the orange box at the bottom right. This is the challenge. We are dealing with a raw dust burden of 18 to 20 gram per normal cubic meter. In furnace this size, that is not just dirt, it is a massive material handling and a metallurgical load. This material or burden dictates the kinetics of our entire gas cleaning system. If we don't manage this specific gravity and the particle distribution correctly, we risk catastrophic scaffolding and poor hot metal quality. This envelope sets the stage for the physical separation process we are about to analyze. This high dust load moves directly into the separation architecture designed to handle these specific volumes. So let's follow the orange flow line on this schematic. The raw gas enters the primary cyclone first where the centrifugal force capture roughly 50% of dry mass. This is your coarse fraction. The gas then enters the gas conditioning tower. There, in short, we can say GCT, represented by the tall vertical vessel with the internal baffles. The GCT uses bend to drop out, oversize agglomerates, and regulates temperature to a target of 100 to 250 degrees Celsius. This thermal regulation is critical for the pressurized baghouse downstream, which uses needle-filled filters and dry lime injection. Finally, look at the green component on the far right, the top pressure recovery turbine. Because we are using a dry system, the gas remains pressurized and clean, yielding a 20 to 35% increase in power generation compared to legacy wet scrubber. This energy recovery is a direct result of our physical separation efficiency. This architecture creates a very specific physical split in the captured material. Now, the Result of our process architecture is what I call the 50-50 physical fracture. On the left of the screen, you see a pile of primary coarse dust. It's a robust 7 kg pattern of hot metal with a median diameter of 80 to 120 microns. This material is highly flowable with a low angle of repose. Now look at the blue tinted pile on the right, the secondary fine dust. It's also 7 kg per ton, but the teeny, typically 5 to 50 micron. So notice the density difference. The coarse dust is heavy at up to 1800 kg per cubic meter, while the fine dust is a fluffy 400 to 800 kg. This high porosity cohesive powder requires sealed pneumatic transport because its angle of repose exceeds 50 degrees. Understanding this physical breakup is mandatory for designing your silo and conveyor system to avoid blockages. Beyond the physical size, there is a complex thermodynamic reason why the dust is split this way. Why does the fine dust carry the tramp element? Look at the cross section of the furnace throat. We have a zinc circulating loop. In phase 1, in the high temperature zone above 1173 Kelvin, solid zinc volatiles into gas. The reaction governed this behavior. As the gas rises in the phase 2, it oxidizes and condenses onto the cooler descending burden. However, in the phase 3, the escape, the thinnest or finest condensed zinc oxide particle fail to adhere to the burden. They are swept out in the top gas, bypassing the primary cyclone and migrating almost entirely to the secondary baghouse. This migration is why the baghouse is not just a filter, it's a chemical concentrator. If this loop is not broken, the internal circulating load will eventually lead to lining wear and operational instability. To quantify this migration, we must look at the specific chemical specialization in each fraction. Now, this diagnostic matrix is our cheat sheet for recycling. The orange column shows the coarse fraction, which is an iron rich treasure, 35 to 50% total iron, mostly as hematite and magnetite. Its zinc content is negligible at zero point 0.1 to 0.3%. Now look at the teal fine fraction column. The iron dropped significantly, but the volatile zinc spiked to 1 to 3.5% and sometimes as high as 5.67%. Now the calcium oxide at the bottom is it's elevated in the fine fraction up to 14.2% because of our dry lime injection in the baghouse. This chemical breakup tells us exactly where the bad actors are. We can recycle the coarse streams easily, but the fine stream requires a specialized processing because it is a primary exit point for alkali and heavy metal in the furnace. The form these chemical take in a dry system gives us a massive operational advantage over a wet pit system. This is the so what factor for your plant bottom line. In a legacy wet scrubber, the zinc is trapped in a wet sludges and a zinc ferrite. This is an insoluble trap that requires massive water treatment and high temperature roasting to recover anything. Now look at the bottom section. Modern dry GCP through a speciation shift. The zinc is captured as soluble zinc carbonate and zinc oxide. This is the resource enabler. Because these phases have a high solubility, we can use direct ambient acid leaching for extraction. We eliminate the moisture. eliminate the water treatment overhead, and turn a hazardous waste into a sellable chemical byproduct. This shift from ferrite to carbonate is the single biggest advantage of the dry breakup in a 1050 meter cube furnace. Finally, let us see how we close the material loop using this distinct stream. We conclude with the engineered recycling pathway. Follow the green circular loop. The coarse Fe by C recovery stream goes straight to the sinter plant. Its high carbon content replaces coke grease at a 1.0 substitution factor, and its low zinc protect the furnace from scaffolding. For the fine volatile processing, we have two options. Option A is the hydrometallurgical route we use discussed acid leaching to extract zinc for the external sale. Option B is the Brex briquetting, where we use vacuum extrusion and organic binder to create high strength cold bonded briquette for direct furnace charging. By utilizing this pathway, a 1050 meter cube furnace can achieve a near zero waste profile. We have partitioned the dust, managed the thermodynamic, and utilized the speciation advantage to protect our equipment and maximize the yield.